Hello, and welcome to the Robot Design and Construction Tips presentation. Today I'll be talking about some general tips for designing and building your robot. These tips are generally applicable to any year's competition, so I won't be talking about anything specific to this year's game. So first of all, a reminder up front that all of the information that I'll be presenting today you can find on the Best National Registry. Of course, you'll need an account on the registry, and then you can just take a look at your team workflow. And in there, you should be able to find this presentation file, as well as the other Kickoff breakout session presentation files. And also you can find links to this recorded video and the other breakout session videos, which are all on our Rocky Mountain Best YouTube channel. My name is Ben Straub. I'm an electrical engineer with Northrop Grumman. But I also volunteer with Rocky Mountain Best and the Denver Best competitions. Right now I mostly focus on live streaming aspects, but I also have some experience building robots and things like that. So today I'll be talking to you about robot design and construction tips. Here's a quick overview of some of the things we'll be talking about during this presentation. We'll start off with the engineering design process, which I think is always a good starting point for framing your design. We'll also talk about subsystems and system integration, how all that works. We'll talk about communication and documentation. Those are kind of intertwined and they're really important and often get forgotten. Design engineering and math examples, we'll go through some of those to give you an idea of some of the things that you can actually put into practice. And then finally, we'll move on to the construction tips. We'll talk about tips for how to use materials, the various materials that you'll have, as well as some fabrication tips and some safety advice. So let's start by talking about the engineering design process. So the engineering design process is a methodology or really just a way of thinking and a way of approaching a problem. And when I say problem, that can be just about anything. Anytime you want to design something, or you want to build something, or you just want to do something, you can approach it using the engineering design process. You just have to kind of frame up, what it is that you're trying to accomplish, and you may have to tweak the process a little bit, but the same kind of ideas can be used on a lot of different things. And so, you can use that, for your robot as a whole. You can kind of frame the whole thing using the engineering design process. You can use the engineering design process on individual robot components. So you could, go through the engineering design process cycle for, say, your arm or your drive base or something like that. Your engineering notebook can also be approached using the engineering design process. Software design, which is part of the engineering notebook, also you can use it for that. And marketing presentation, that doesn't even, people might say like, oh, well, that's not even an engineering problem, but you can approach all of it with the same sort of mindset, and we'll talk about what that is in a second. But some of the reasons why you might want to use that, for one thing, it helps maintain objectivity. So what that means is it's a way of fairly, evaluating different ideas. So what can happen sometimes is, you're meeting with your team and everybody has some different ideas. What can happen is that you may have one person who is just, more vocal at, sharing their idea than other people. But they may not have the best idea, but what can happen is if you're not kind of looking at everything and evaluating it fairly, what can happen is that it ends up just, the person who talks the loudest ends up with their idea going forward. The engineering design process kind of sets up some things for evaluating things fairly, so you can kind of avoid some of that issue. The other thing the engineering design process helps with is identifying problems early. So you test. There's we'll go through the process in a second here, but the way you test things early and prototype, and even just evaluating the problem from the beginning, can all help make sure that any issues you run into them early, and you can fix them before you spend too much time spinning your wheels on something. Okay, so here is that actual engineering design process. This is the version we like to show, but you may see a couple different versions of it, but they're all generally the same idea. They have the same sort of concepts to them. You can use whichever version you like, whatever best fits whatever your problem is or whatever your team's working on, but they should all have these same general concepts. So the first step is understanding the problem. This is something that often gets overlooked, but it's a really important step because you need to make sure that you understand what your problem is, what restrictions you have, what requirements you have. And so in your case, with the best competition, you want to make sure that you're reading the rules. That's where all of your requirements are. You need to make sure that you read them very well, understand them. They can be a little complex and hard to follow sometimes. So sometimes it can be really useful to highlight things, print out a copy and highlight it, or make a table, or, make some sort of summary of what you're getting from the rules. And all that can be helpful for this step. Another thing that can be helpful is researching similar designs, or how people have approached similar problems in the past. So maybe your team last year, you can look at the drive base they used, or a lot of times best robots have similar sort of driving requirements. They need to drive around a field and maneuver around obstacles. And so seeing how past years have done that, and even how other teams have done that, because sometimes you can find that online too. All that can be really helpful to give you some ideas to start with. And then, of course, inventorying whatever resources you have so you know what you have available to you to address your problem. The next step is where you start actually exploring concepts and brainstorming ideas. So this is the part where you're really just brainstorming whatever you can, um, for in terms of overall robot strategy and robot designs. You can have brainstorming sessions for, your drive base, or, maybe an arm design or whatever. Don't get too detailed here, but just it's the time for sort of high level ideas and just any concepts that you can think of that might help solve your problem. Um, this isn't the time to be too analytical or critical. Uh, you know, let all ideas fly, even if they won't necessarily work. Sometimes even ridiculous and far-fetched ideas can sort of trigger new ideas in someone else, or they can spark new ideas that sort of build off the crazy one, but might be something more practical. And then at the end of this phase is where you kind of take all those ideas that hopefully you've written down, and you start kind of selecting down the ones that actually make more sense, and the ones you want to sort of pursue further. And that brings us to the analyze and prototyping stage. So this is where you take those ideas that you've selected and you start, prototyping them, modeling them. They can be physical models or digital models. Cardboard can be a really useful tool during this stage because you can, cut it and glue it and tape it quickly, and just make, very simple prototypes. A lot of times, they don't even function, they don't have motors or anything, but just like quick proof of concepts to show what it is that your idea is trying to do, and give an idea of, okay, is this actually feasible? Will it work? During this time, it's okay if things don't work, if they fail, and maybe an idea just isn't meant to be, and it's not going to work for whatever physics reasons or whatever. That's okay. The whole point of this phase is to figure out what is and isn't viable, and to sort of narrow down to, okay, what's the best idea going to be? Which one do we want to actually go with? A really useful tool for analyzing your different options can be something, some people call it a structured decision making matrix, or a trade studies, basically the same thing. And pretty much what this is a table where you have different criteria that you evaluate your different options on, and you give them a score. And the different criteria have different weights, and you sort of multiply the weights by the score and add it all up. And it can give you sort of a number that you can actually compare for each of your options. And so this can be like a really great way to fairly evaluate your different options. It can also, it's a really great thing for us to see in your engineering notebook, so we know how it is that you arrived at your decision. It's also really useful to keep written down and keep track of, because you may find out later in the process that whatever idea you went with didn't actually work or failed for some reason, and you want to go back and reevaluate options. Well, if you still have that design decision or trade study that you did earlier, then you can just sort of modify from there and pick up where you left off. So that can be really helpful. And then the whole result of all this phase should be narrowed down to your top idea, or one or two top ideas that you're going to pursue for actually building. So then in the detailed design and manufacturing phase, this is where you're actually building parts of the robot. At this point, you should have a pretty good idea of the overall system design, and so you should have an idea of how you can divide things up. So a lot of times this is kind of divided into a drive base and an arm or end effector or grabber, and then the software also is another important component. And by dividing it up, everybody can sort of work on their parts at the same time and work on them in parallel, and actually start building things. It's also a good idea to do additional detailed designs before you start cutting things up or anything like that. Really working out the details, building the thing, and then that gets you ready for the next step, which is to put it all together. So that step is called integration and test. And so like I said, you're putting all the individual components together into one larger system. And we'll talk about that even in more depth in a second. And then once you have everything together, you're testing it. And the testing is listed here in this step, but I really like to say that you should be testing the whole way along as you're building things. Prototyping is all about testing things at a very early stage. As you're actually building things, it's a good idea to sort of test the little bits that you can as you build it. So yeah, you should really be testing all along, but this is where you do the big overall system test. Like once you have everything put together, you can start driving the robot around. It's a good idea if you may not be able to build the game field necessarily, but you can build things that are the right size or shape. Make them out of cardboard or whatever, just so you can make sure that the robot is actually able to reach the things it needs to, and lift things it needs to, and for that, you may want to make sure that you have the right weight, things like that. Whatever you can do to test as much as you can ahead of time. And also, this is a good time for your drivers to get lots of driving practice. So what happens if things don't work the way they're supposed to right away? That's pretty normal, actually. A lot of things don't always work perfectly the first time, and that's okay. The whole point of the engineering design process is to be an iterative process. That's why on the left you have the arrows going back to earlier steps, It's because things don't always work, and so you need to refine things. You need to see how you can make things better. Maybe it works somewhat, but it could be better. Um, this is the time to tweak things and go back as you need to the earlier steps. Um, how early do you go? It depends on what sort of you know issues you're having, what sort of failures there are, and what could be better. You may get to the end here, and maybe there's something that's not in compliance with the rules, or maybe your arm isn't long enough to reach whatever it is that you needed to reach, and so you can't accomplish the goals that you wanted. And you need to go all the way back to the original, to step one, to understanding the problem and figuring out, okay, what is it that went wrong? What did we not understand? Um, Maybe you need to brainstorm new ideas. Maybe you just need to go and reevaluate the ideas that you already had. So yeah, this is the point where you iterate, and maybe you don't have that big a failure. Maybe you have something that works pretty well. Um, there's usually something you could do better, and so you can, even if you have a good design, you can try out improvements. You can do additional prototyping to see if there's something that could make it work a little bit better. And finally, we have delivering the product. That step, it's not even actually shown on the diagram to the left, but this is important to keep in mind that at the end of this, you're producing a product and you're kind of delivering it in the sense that with your robot, you're taking it to the competition, and you've got to actually compete with it. And with the engineering notebook, that's another part of the product. You're not allowed to compete without submitting an engineering notebook. It's a mandatory part of Best Robotics, and so making sure that you don't save that till the very last minute to put your engineering notebook together. If you document all these steps that you've done as you go along, like your prototypes and your trade studies and things like that, the engineering notebook should be easy to put together. So yeah, that's the engineering design process, and you can kind of sort of start to see how this could be applied to a lot of different things, more than just the robot. So for example, if you're competing in the best award and you're figuring out how you want to do your marketing presentation, you can apply these same things. Like, you have to understand the rules of the marketing presentation. You can brainstorm different ideas about how you want to, structure your presentation. What sort of format do you want to use? Um, you can sort of prototype. That one's like a little bit, you know, iffy about how well it applies, but you can certainly try different formats and things like that in that stage. You put your presentation together, and then integration and testing. So testing would just be practicing your presentation and have people listen to your presentation, and they can use the same score sheets that will get used on you by the judges, and they can evaluate you, and you can see how you did and what you need to adjust, what you didn't have in your presentation, and then go back and add those things and repeat the process. So here's a little more information about system and subsystem integration and how all that works. Um, so a common way to sort of divide up your system is, you'll have a drive platform or drivetrain or drive system, whatever you want to call it, that's concerned about, how you drive around the field. You probably will have wheels, maybe you have a skid or something else, or a caster, and how you control your speed and position and all that sort of thing. Then you have the sort of end effector, or this may be an arm. It may have sort of a grapple or claw or scoop or something on the end of it. You may have more than one of these, and you could divide it up into the arm and then the actual gripper. But this is it has its things that it needs to do, like rotate around, move up and down, grip whatever it's gripping. if you're trying to lift something, it needs to be strong enough to lift it, all that sort of thing. And then the actual programming of it, which is also really important, not just because, you need to be able to control it, but you need to be able to control it well. It's always a good idea to do as much as you can in the programming to make it easy for the driver to drive. And so, having a well thought out control scheme and well done programming can really help out your driver and help your team out as a whole. So, you can have different sort of sub teams working on these different pieces, and then for integration is when you actually put them together. You put the arm on the drive base, you load the programming, and connect all the electronics to whatever ports they need to be in, and you can test it from there. Don't feel like you have to be limited to this sort of subsystem breakdown. You can divide it up to whatever makes sense. If you have a big team and you feel like you can divide things up even more, then great, go for it. Or even just you have somebody who wants to focus on some small piece, whatever you want to do. You can divide your subsystems up into subsystems. You could have part of the drive team that just focuses on manufacturing the wheels, because that can be a whole topic of focus on its own. So here I'll talk about some of the best practices for communication. Communication is really important, especially if you have bigger teams, or if you have things broken up into different subsystem teams. It's important that you have communication within your subsystem team, but it's also really important to have communication between groups and between teams, to make sure that you don't end up with a situation where the ARM team didn't talk to the drive base team, and now the ARM doesn't fit on the drive base because there was some communication issue there or something. So you want to make sure that you're communicating with each other. That means not just traditional talking to each other and things like that, but also sort of documenting interfaces between things. So documenting if you have like a wiki or something like that, or a Google Drive where you keep your documentation. All that is really great to have, and a really great way to help communicate between teams. Social media can also be an effective tool for communicating. That includes not just, so you may be thinking like communicating to your community and things like that with your Facebook page or whatever. But you can also use that as a way to communicate between people. So maybe you send, you have a group on your social media that's, your robot team, and you can have group chats there. There's also a lot of really great collaboration tools that you can use, like there's Slack or things like that, where you can have different discussion topics and ways to communicate with each other. Scrum is a concept that comes from an industry. There's like Agile methodology, and the Scrum part of that is just the sort of the daily stand-up meetings. They call it stand-up because they're supposed to be really short meetings, and so if everybody just stands up for the meeting, then people aren't going to talk for a really long time because they don't want to stand up forever. But yeah, this is just supposed to be short, quick meetings about what the status is of whatever it is people are working on. So you can say what have you accomplished since you last met, or what have you been working on? What do you plan to work on next? And are you having any issues or roadblocks? Do you need any help? You're all working as a team, so if somebody needs help with something, it's really important to help them with that and make sure they get the help they need, so that you don't get to the end and it's like, oh, well, the drive base is great, but the ARM doesn't work at all because, so-and-so needed help and we didn't help them. So having a daily meeting, you can have a daily stand-up within your team, and then you could have another daily stand-up of just the team leads, is one way you could organize that so that you don't have, everybody all listening to 30 different people talking. But it's really all about whatever works effectively for your team, and so you'll just kind of have to see how that goes, and what makes sense for your team and your team size. Some other things that are good to think about and figure out with your team, and this is something that hopefully you've kind of been figuring out even before the season started, is how does your team resolve disagreements and conflicts? Do you put things to a vote? Sometimes that works, sometimes it doesn't, because sometimes it's people don't always vote for the best option. So figuring out how are you going to resolve those sort of conflicts. And like I said, it's about what works for your team. In terms of documentation, that's really where the engineering notebook comes in. That's the place, that's the final place where all your documentation should be ending up, because that's where we want to see it. In the interim, you can definitely put pieces of documentation, on a Google Drive or on a team wiki or however you want to do that. And that can be a really easy way to document as you go along. So, maybe each individual team has their own sort of documentation page where they can kind of keep track of things as they go along. And then at the end, you can sort of put it all together. But really, once it all comes together, it should be sort of the full story of how did you decide on your robot? Like, how did it come to be? What brought you to that design? How did you implement that design? And all that sort of stuff. Like I've already said, the documentation is important to the engineering design process, and just engineering in general. It's important for a few reasons. For one, it's an important record of the process you use to get to your end product. So it can be a good historical record, and you can see if something went wrong, you can see, well, what went wrong, how did we get here? So it could be useful for that. Like I mentioned on the last slide, it's really useful to have as a communication means between groups. So if you document, this is how my arm is going to attach to the drive base, then the drive base knows, okay, we need to make sure we can accommodate that. And it can be a checklist against requirements. So if you've documented what your requirements are, and you've documented, what you've built, you can, check those off against each other. And also it can just be a really important, really useful way to bring new people up to speed. So maybe you have somebody that had to miss a week, or maybe somebody joined the season late. Then you should have documentation as you go along so that they can read that and say, oh, okay, this is what you're doing. This is what the design is. I understand. And they don't have to have been there for the original talks, but they can get it from your documentation. And as I've already mentioned, the engineering notebook is mandatory. You must submit an engineering notebook in order to compete, and that is due on practice day. You can see the exact time and date that is in the BEST National Registry. It should show up in your deliverables, saying that you have to deliver the engineering notebook. So you can check that out there. But yes, make sure that you submit that, because if you don't, and you don't turn in your notebook, you will not be allowed to compete. Okay, so changing gears a little bit. Now we're going to start talking about some actual examples. And we're going to start off with some math and how you can use math effectively to really save yourself a lot of time and a lot of resources. So just as an example here, we're going to talk about torque. And so torque is really a force applied around an axis of rotation. And that's important because the different motors that you have different torque limits, like the motor's supply torque. And so that can tell you, how much weight can your arm lift up and things like that. So here's just a really simple arm example here. So they have a 2-foot long PVC pipe as the main part of the arm, and they've got a little gripper there that they say is, half a pound. And this example is from an old year where they had cargo balls, but that could be really anything, and they're saying that they need to lift up 0.4 pounds for that. And they've figured out how much the PVC pipe weighs as a per foot measurement. So you could just, measure that yourself on a scale, or you could probably look that up in a data sheet somewhere. So those are all of our measurements. So to get the torque required for each piece, it's the weight of the piece, times the length away from the axis that it is. So for the PVC pipe, that's 2 feet, so that's 0.41 pounds. And the center of that PVC pipe is 1 foot away from the end that it's rotating around. So you multiply that out, that's 0.42 foot-pounds. The gripper and the ball are both 2 feet out, so you multiply those weights by 2 feet. And you add all of it up, and you get 2.22 foot-pounds. You can convert that to inch pounds, which is the units that you'll probably see for your motor data sheets. And so that's 26.64 inch pounds. Well, then you go and look up the torque that large motor can supply, and it's only 23.53 inch pounds. So that's bad. That means your large motor is not going to be able to raise that arm up while it's holding that cargo ball. And I would add to that, even if those numbers, even if the required torque ended up being just below that motor torque, you really want some margin in there too, because if they're basically the same, then it's just gonna stall there, and it's not gonna lift it very quickly, or it would be really slow. So in this case, it would be, back to the drawing board. Can we come up with a different design? Maybe you could make it shorter so that it doesn't need to lift as much, like out as far away from it. That'll reduce your torque. Maybe there's something you could do, like, to make your gripper lighter, or make the PVC pipe lighter by, drilling a few holes in it. But then you have to make sure that you're not gonna, jeopardize the structural integrity of it. But you can see by doing the math ahead of time, you don't have to build the whole thing just to find out that it can't lift it. You can, do the math and say, hey, this isn't going to work. Let's come up with something else. Here are the specs of the motors that you have shown for you here, just for quick reference. But you can also find all these either you might be able to get the data sheets on the registry. I'm not sure if those will be there, but you can also definitely just Google the part numbers for your motors, and you can find the data sheets online really quickly, and they will tell you these max torque numbers. Here I just wanted to tell you about another part you have at your disposal, is the potentiometer. I just wanted to highlight this one because it doesn't get a lot of use, but it can be useful at times. I think a lot of people don't understand it very well, so I wanted to talk about it. And so that's the potentiometer, and some people could just call it a pot for short. But it's a device whose resistance changes as you turn the knob on it. And so you can use it to make an analog sensor that can measure an angular position of something that rotates, like a robot arm. So you can put it along that axis of rotation and have it turn about that, and then you can connect wires up to the potentiometer, and actually measure as it changes, like as it rotates, so that your software can have an idea of where the thing is rotated to. So that can be useful if you want to put in software limits of where it turns to. You can keep it from turning beyond a certain point just by reading that potentiometer. You can have the software cut the motors off if it goes too far. It can also be useful if you want to sort of automate some tasks so that a driver doesn't have to manually do it. So let's say you want to have a button that automatically rotates your arm 90 degrees. Well, if you have a potentiometer there that's connected to the axis, then you could see what the current angle is, and then take control of the motor and turn it until it gets to the new angle that you want, and then tell it to stop. And so doing automated things like that can make the driving a lot easier for your drivers, and that can help you do better in the competition. It can make things quicker. So some of the software you have available. So there's Simulink, that's a MathWorks product. So you can get that through MathWorks for free. EasyC is a pretty common way that people use to program their Cortex. There's also RobotC. EasyC this year, the licenses weren't provided by Intelitech for free, but you can get a discount. But some of the hubs are paying for licenses for teams that want it. So just talk to your hub and see what they're doing if you want a license for that. And those are all programming options. For actually, doing CAD, so like drawing things up, there's SolidWorks, Inspirotech, HSMWorks. These are all options. For doing math, you can obviously kind of do it manually, but they also have this thing called Mathematica, and that can do a lot of like really cool math for you, and you can kind of describe what it is that you want to do, and it's a pretty smart tool. It can be useful at times. I think you can also like sort of try it out online on like Wolfram Alpha, so you can definitely give that a try if you want. And the instructions for how to actually download those things should be available on the BESH National Registry. So just go see your team workflow once you log in there. Okay, so moving on to the actual construction tips, which is what I know a lot of people are interested in. So I've kind of divided this up into the materials themselves, and then some actual fabrication tips and safety tips. So for your materials, you've got the plastic sheets, so like the polycarbonate and PVC sheets. You've got some aluminum parts, like there's the aluminum flat bar, and there's an aluminum sheet. You've also got a steel threaded rod and some piano wire if you want to use that. There's a good amount of various wood things. There's some wood plywood and a wood 1x4. You also have some PVC materials in your kit, so there's some segments of PVC pipe along with some T's and elbow pieces. And then there's a whole bunch of hardware parts like hinges and brackets and things like that. There's also electrical components, wires and switches and things. And then you've got a bunch of different types of tapes and adhesives in your kit as well. For fasteners, there's a whole bunch of different fasteners of different sizes, so things like screws, bolts, nuts, washers, things like that. And then finally, there's a bunch of other random miscellaneous things like twine, rubber bands, Velcro, paper clips, just a bunch of different stuff. This is all a very high level general list, so if you want to see the full list, you should really be going and looking at the rules document, and in particular look at the consumable kit section of the rules, and then there's also the returnable kit section of the rules for the returnable parts. So for the plastic sheets, so there's a link to a video there that talks about cutting plastic sheets. So if you want more information than what I give you here, you should definitely go look it up. You can also Google this kind of information on your own. One thing I want to tell you right up front, and that you'll probably hear me say quite a few times, is make sure you're wearing eye protection. Plastic especially can chip or melt and have little bits, like melty bits of plastic fly out while you're cutting it. And all that stuff is really bad you don't want it in your eyes. So always wear eye protection when you're cutting things or working with power tools or anything like that. And then also make sure that you're securing your work. Don't try to cut something while it's loose and flopping around. Clamp it down to a sturdy surface, or put it in a vise or something, something to hold it steady. So yeah, a couple different options for cutting plastic. One option that is pretty basic but can work well is just basically cutting it with a knife and then breaking it. This is good for like really thin sheets. You can just use a straight edge, cut it with a utility knife or something sturdy, and usually you'll kind of make a score along it the first time. And if you have a nice deep score, you can put a solid edge, like a straight edge or something, along that score line and break it off all at once. So that can work well. Another thing you can do is a jigsaw, and so that's like a pretty simple, low effort, low barrier to entry tool. It's just a handheld saw. You should, if you don't know what a jigsaw is, you can look it up, but it's got just a little oscillating blade on it. So you can use that. Just go slow with it. Use this is the recommended teeth per inch. There's 10 teeth per inch, but you can see the blades will sometimes say if they're good for cutting plastic or something like that. Again, you want to make sure that your workpiece is really well supported in that case. Otherwise, the jigsaw may kind of like break pieces off. You can use a bandsaw or a circular saw or a table saw. And similar sort of things for all these. I won't go into too much of the details here, but it's here for reference. Just know that with some blades, and when it's going really fast, it can actually melt the plastic as it cuts. It's not a bad thing necessarily. Just be aware of that. For cutting the aluminum, so this is specifically talking about here the aluminum bar and aluminum rod. So those are the thicker pieces of aluminum. So there are several different ways you can do it. A hacksaw is actually, I think, a really good way to do it. Sure, it's a little bit slow. You've got to put in some muscle power for it, but it's safe. It's pretty well controlled, and you don't need a lot of like special equipment for it. So I've done it this way before. I've cut it with the hacksaw, and it'll work. Just make sure you have a good blade for it. And they make metal cutting blades for hacksaws. You can use a jigsaw too. They use a metal cutting blade for that as well. Bandsaw, you can get away with a wood cutting blade on that, or if you have a metal cutting one, that works too. Or a horizontal bandsaw if you actually have one of those. So yeah, these are all options you could use. But like I said, I like the hacksaw personally. Um, Again, with these, make sure you're wearing eye protection, and make sure you're securing your work. Uh, you don't want little bits of hot metal flying out and hitting you in the eye or anything. Um, yeah, you should be able to cut that. And aluminum in general is not it's a really soft metal, so it's relatively forgiving and relatively easy to cut for being metal. For the aluminum sheet, because that's going to be like a really wide and thin sort of thing. Um, you're probably not going to want to use those tools I just talked about for the bar and the rod. For this, you probably want to use something more like if you have tin snips, you can use those. It can take a little bit of time to work your way through it, but it should work. It might sort of bend or deform the edges a little bit as you cut, but you can make it work. They also have like sheet metal shears. They have like manual ones that you can sort of crank down and cut along a straight line, or they have like power tool sort of things. They're basically like power tool scissors that you can kind of cut through the sheet. Um, However you're cutting it, it's a good idea to mark it. As you know, you always want to mark it. You can use a Sharpie for that. You can also like just score a line along it. That can work too. Um, and after you've cut it, and this goes for the previous things too, I should have mentioned, but you want to kind of clean up the edges. So with the metal, you can use a metal file to clean up the edges so there aren't any sharp burrs on it. With things like plastic or wood or whatever else you're cutting, you can clean it up with a piece of sandpaper. And you can use some of that for metal too, to soften the corners a little bit. But a file works pretty well for cleaning up the metal edges. Sometimes you may want to bend pieces of aluminum. So they have these special bending tools. You can use like this the sheet metal brake. Here is the big thing shown there. And that gives you like a nice edge to bend along, and it can help you with the bend there. They have like hand bending pieces, but also just like a vise can work really well for that. If you see that picture down at the bottom right, that gives you an idea of kind of how you want to situate everything. You want something that's gonna, you want kind of like flat surfaces on both sides of the bend, to help you bend things and keep it straight where it's not, where it's supposed to be straight, and just bend around the part that you want. Do note that if you do too tight of a bend, like if the radius of the bend is too sharp, you can't actually break the aluminum. It'll just snap. So it can be helpful to put something like a dowel rod or something rounded in there, like in the inside of the bend that you kind of bend around, so that you have a nice gradual curve, and that can, keep the metal from breaking. Okay, so for PVC pipe, you can, of course, use a hacksaw to cut that. That's what I personally use whenever I need to cut PVC. And that can do a pretty good job of getting you a nice clean cut on the PVC. They also make these things called PVC cutters, and that's shown in the picture there. And those are designed for cutting PVC, and they're super quick to use and easy. Sometimes they can kind of, make the edges a little rough, and the hacksaw can do that too sometimes. So once you cut PVC, if it's an edge that's going to be exposed, then it's a good idea to clean it up with a piece of sandpaper or something to smooth it off. But if it's going to go into a PVC connector, then it doesn't matter. Nobody's going to see it. Nobody's going to care. So you don't need to in that case. Um, for wood, and we'll get into more detail here in a second, but with round parts and holes that you want to cut, you got drills, drill presses, and hole saws are all options. So this shows a drill press. Drill presses are nice because they give you nice, perfect perpendicular holes. Um, they're also really nice because they usually have some sort of speed control that you often don't get on a hand drill. Um, and yeah, they're a lot more sturdy and yeah, they can do a lot more than a hand drill can, or do it a lot cleaner. Um, so yeah, if you don't know how a drill press works, it's got the drill there. You've got your spindle and your chuck. You put the drill in it, and then you turn it on after you've set your speed, and then it has a little metal crank there that you kind of turn and pull it towards you, and it pulls the whole top down, or some of them designed to pull the table up. Um, but yeah, it brings the drill down to the thing you're trying to drill in, and yeah, and it drills the hole. Whenever you're using this, you need to make sure that the drill press is secure. I mean, they usually do have like a heavy weighted base, but it's a good idea to have that either bolted to a table or, I mean, depending on the height of it, maybe it's bolted to the floor or something like that, so that it's not going to like tip over while you're using it or something. Also shown in this picture on the right, you have a couple examples of hole saws, which are basically just big circles, like it's sort of like a saw blade that's wrapped into a circle. And so those can cut you a nice clean circle out of a piece of wood, which can be great if you're making little wheels out of it. Um, or it could be a way to, if you want to make like a wooden gear or something, you can start with the circle and then, um, measure out where your gear teeth need to be exactly, and you can get templates and stuff for that on the internet. But you can start with the circle and then cut out the teeth from that with a jigsaw. And then for drill presses, I've added this table here. Um, and this is just for reference, but you can find this online. And a lot of drill presses, at least that I've seen, they'll have like a little table like this for reference, like either taped inside the cover of it or something like that, so that you always know how to use it. But um, in general, smaller things, smaller drill bits, you can go faster. Bigger ones and hole saws, you need to go a lot slower with them. Um, and Yeah, the other thing here that's not really mentioned is with some metals, you usually need to, well, at least with the harder metals like steel, you're going to want to use some sort of cutting fluid. Um, so that's basically just like a little lubricant that will keep the drill bit cool and keep it from overheating and deforming. Um, Aluminum, you can get away with not using it because it's pretty soft, but a lot of times it's just a good idea to use it anyway because it'll make your drill bits last longer. For stuff like that, just ask your mentor what kind of stuff you guys do with that, and they should be able to help you with that. For drilling, and this is especially true if you're using a hand drill, but it's a good idea to center punch your holes ahead of time. And so what that does is it just puts a little divot there that the point of the drill can rest in when you get started. Otherwise, the drill has a tendency to wander, is what they call it, or walk around a little bit before it really starts digging into the material. Um, and so they make like center punches are really cheap. You can get them. There's like spring-loaded ones or ones you just hit with a hammer. Um, You can sometimes get away with just using a nail or something like that, but it's a good idea to have like an actual center punch. Um, and you want to make sure you just give it one good clean whack. You don't want to like sit there and hammer it with multiple hits, because it can kind of bounce around and make multiple holes, which is, kind of defeats the purpose, because then it can, the drill can go from one hole to another, and that's the whole point of this, is to keep the drill from moving. So, um, yeah, and then clamping your work is always a good idea. If you're using the drill press, you need to make sure that it's clamped down to the table that to the drill press table. A lot of times there'll be like a vise or something attached to that already that you can use, but if not, you can clamp it down with just normal clamps. So for fasteners, and I'm talking about screws here mostly. Um, so a lot of times it makes sense to pre-drill screw holes in like your wood and stuff like that, so you don't split it. But if you want to tap a hole, then you kind of have to be particular with that, with getting the right drill size and the right tap to match the screw. So what I'm talking about here, what tapping a hole means is basically you're taking a hole and you're using this tap that it will actually cut threads into the hole, so that when you're done, you can then screw a screw into it. And you don't necessarily need like a nut on the other side or anything like that, because the screw will fit perfectly like where it has to screw into it. And you can get a lot of times these will come in sets where you have taps and the corresponding drills that go with them, so that the drills are the right size for the tap, and you can get those at a hardware store. Just make sure when you are tapping it, you can kind of see it in that picture on the right, it's a little T-shaped part. A lot of times you'll need to, go in a little bit and then back it back out, so that it can remove the bits of metal that's kind of cutting out as it goes along. Otherwise, that metal can fall into the bottom of the hole, or it can get kind of stuck in the cutting surfaces, and then mess up your threads. And then also sometimes it's good to use cutting fluid on this also to keep the tap cutting surfaces sharp and all that. Okay, onto some electrical components. Make sure everything is properly connected, first of all. I'd say, make sure polarities correctly, matched up correctly. So that means, red to red, black to black, that sort of thing. Also, making sure everything is secure in its connection too, so it's not, gonna fall apart when it shakes a little bit or have a intermittent connection. And another recommendation is mounting your Cortex unit somewhere where you can easily get to it. That doesn't necessarily mean it needs to be exposed, because sometimes if you put it on the very top and it's like wide open, then sometimes that's a bad thing, because a piece of the field or something could fall on it and knock a wire loose, and that's bad. But if you're putting it kind of inside a compartment, just put like a little door or something on it where you can easily access it, and access it quickly, so you don't have to take your whole robot apart to check a connection or do something like that. Here's another nifty little component called a limit switch. And these are just little switches that you can have your code read it as a 1 or 0, depending on whether it's pushed or not pushed. And this can be a way to, have software controlled limits on, how far an arm can rotate, or, how to tell if your robot has bumped up into something that, you might not be able to see from the spotter's box or the driver's box. For mounting your motors, you get these little motor mounting kits, as part of your consumables, and they're specifically designed to work with the motors that you're given. They start out flat, like you see in this picture, but they can be really easily bent. They're designed to be bent. Just put it in a vise or something on a straight edge, and just bend it like around the corner of that straight edge along those lines you can kind of see along them. Don't try to rebend these because they're only designed to be bent once, really. So there's kind of two different options. I mean, you could kind of mix and match a little bit, but the two main ways of bending these are either sort of inward, where the little parts at the very bottom go in towards the motor, or you can have them outward, like external, where they bend away from the motor. Outward, if you have the room for it on your robot, is usually easier because that means you can get to the screws and you can like screw those screws on the mount without having to take the motor on or off. Because if they're inward, then they're kind of hidden underneath the motor, so you'd have to take the motor off first. But yeah, if you bend it one way and you decide you want the other way, then it's too late. You can't really rebend it. You kind of stuck with what you got at that point. Then this is just a link to a video that Inglewood High School put together, and you can find this on YouTube. I'm not going to play it here, but yeah, if you go and pull this presentation from the registry, you can get a link to this YouTube video, and they just talk about how to build some basic wheel hubs, and it's a really interesting sort of video. They show how to use a tap, like we described earlier, to put the screw threads in, and how to measure it out and build the wheel hub. You also have wheel hubs supplied in your returnable kit, so you can use those too. But if you need additional wheel hubs or something like that, knowing how to make these can be a really useful skill. That's pretty much it. That's about all we have time for. I'm just going to leave you with some of these references. There's links here that obviously you can't get from this video, but if you go and find this presentation on the registry, you can click these links. And the first links for those motors are to the actual VEX page, where you can find, like, you could buy the actual motor that you're getting from Best. But it also has links on that page to things like spec sheets and other useful information. And then that second link is the actual spec sheet. There's Best has a generic kit usage guide that can be pretty useful. So check that out. That might also be on the registry, I'm not sure. And then there's some other documentation for the VEX Cortex and joysticks. There's like the user guide there, or there's a pinout guide for the Cortex, and those are both useful to have also. And then a lot of this stuff you can find just by Googling. Just look for your whatever part number it is. The rules has the part numbers and provider for most of the parts in your consumable and returnable kit. So that's plenty enough information that you can go and Google and find the exact data sheet or spec sheet for whatever it is you want to find more information about. So thank you for listening to my presentation. Hopefully you got something useful out of it, and you might have learned something. Just a reminder, again, this presentation file, as well as all of the other breakout session presentation files, you can find all of that online on the Best National Registry. So you'll need to have an account there first. So students, you'll need your parents to make an account for you, and then just go and access your team workflow. If you have trouble accessing your team workflow, you can also ask your teacher to make sure that you have access to it. But yeah, once you have access to that team workflow, you should see there's files shared with your team, and it should have all of these presentation files along with a lot of other very important files that you'll want. Things like logistics plan and team handbook and all sorts of good stuff. So go and check those out. And there'll also be links to these YouTube videos where you can go and watch them at any time throughout the season. Thank you.